Good afternoon and welcome to RTDology, Burns Engineering's online training series. I'm Jeff Wiggin, National Sales Manager at Burns, and presenting today will be Bill Bergquist, Senior Applications Engineer. Today's presentation, Measuring Temperature in Small Diameter Lines, is part of our continuing series of web-based training modules designed to help you better understand temperature measurement and achieve your measurement goals. If you've joined us for any of our previous sessions, we'd like to welcome you back. If you're a first-timer, welcome, and when you get a chance, do go ahead and check out our previous presentations on the RTDology page at burnsengineering.com. Before we get started, just a few housekeeping items. First, to respect everyone's time, we will make every effort to limit the presentation and Q&A period to 1 hour. We do highly encourage questions, so please type them into the Q&A section or the chat box on your screen. Typically, that's on the right-hand side of your screen, either upper or lower, depending on how you've got it set up. Today's session is being recorded, and we will provide session notes and a link to the recording to all participants as soon as they're available. So don't worry if you do miss something. We will get that information to you. Typically, that's available within 24 to 48 hours after the session. If we don't get to your question or you need some additional assistance, there will be contact information provided at the end of the presentation. Finally, our goal is to answer your temperature measurement questions and challenges. We've built RTDology around commonly asked questions and issues. However, if you have a particular topic you'd like to have considered, give us a call and we'll see what we can put together for you. That covers the housekeeping, so without further delay, here is Bill Bergquist to help explain the ins and outs of measuring temperature in small diameter lines.
Welcome everybody, and thank you for joining us today. I'm going to talk today a little bit about some of the problems that are encountered with measuring temperature in small diameter lines, and we have defined small diameter lines as anything less than 4 inches. You can start out with a real accurate sensor, but if you don't plan the installation and do the piping correctly and thing, you can end up with some fairly large temperature measurement errors. And these are due to that the biggest error is the result of insufficient immersion of the sensor into the process. Most of the sensors, the more common styles, need at least 3.5 inches of immersion. Thermowell applications require 4.5 as a minimum. There are some things that can be done to get around that, and those are the things that we're going to be focusing on in this presentation. So planning ahead with your piping is important, and knowing what types of sensors are available for small diameter lines is important. Some of the big reasons, to do this is to get to the very best measurement accuracy that you can, and that's going to ensure that you have a good, high-quality product that you're making, a really efficient use of energy, and if you're in a startup situation or revalidating, it makes that process go a lot easier. So today I'm going to just talk about some of the technologies for measuring the temperature, some basic terminology that's used. We'll look at how to select and install the sensors, and we'll look at some of the details of how those installations are put together. First off, the two technologies that we're going to talk about, and it's primarily going to be RTDs. We'll look at some of the features, accuracy, traceability, stability, and repeatability. Those are the big 4 advantages or the main features of an RTD. Thermocouples, on the other hand, they can be extremely durable, really fast response time, and very tip sensitive. So if you have a situation where you're trying to measure a surface, for example, a thermocouple may be a better choice. You are giving up a little bit of accuracy, but maybe the fact that it's more tip sensitive, it may actually end up being a more accurate technology to use. And when we talk about accuracy, It's just the degree of conformity of a measured or calculated quantity to its true value. And of course, when we're measuring things, we can never be absolutely accurate. There's always some tolerance around it. And these error sources can come from interchangeability, and that's just the manufacturing tolerances that are used to produce a thermocouple or RTD. And there's things, hysteresis, drift, self-heating, and maybe half a dozen other error sources. One of the largest error sources with an RTD is the interchangeability. And this is the manufacturing tolerances that are used when these sensors are produced. And there are two main categories of tolerance. There's a grade A and the grade B, and those are defined by the two standards, the ASTM E1137 or the IEC 60751. The tolerance is defined by these equations over here on the right-hand side. And so you can plug in your temperature in degrees C, and it's the absolute value of temperature. So if it's a negative temperature, you just drop the negative sign. And you can find what your interchangeability tolerance is at any given temperature. This is showing it in a graphical form. The tolerance is along the vertical axis here. And right at 0 degrees C is where the RTDs are trimmed or adjusted when they're manufactured. So that's where we have our smallest interchangeability tolerance. And as you diverge away from 0 degrees C, those tolerances get larger. And that gets back to those equations we just looked at. One other interesting thing to see from this graph is that the ASTM standard has a slightly smaller tolerance than the IEC standard. That may be something to keep in mind when you're writing up a specification for an RTD.
Hey, Bill, can you just quickly touch on the difference between Class A, Class B interchangeability at the with the finished sensor versus the sensing element itself? It's something to keep an eye on.
Yeah, there's actually a couple things here. One would be if when you're speccing out an RTD, to make sure that the interchangeability was measured at the end of the lead wires, because in some cases, if you have a 3-wire circuit on an RTD, that cable can introduce some error into that measurement, and if you have a long cable, it can be more of an issue. Shorter cables or just maybe 3 or 4 inch long lead wires, typically not too much of an issue, but just the fact that it's measured at the end of those leads in the completed sensor really is important to know. Some of the basic sensing elements, they're manufactured and they're trimmed to a certain interchangeability tolerance, but then when you build that into a completed sensor, that number can shift just a little bit. And so you need to be aware of that shift by making sure that the manufacturer has measured from the end of the lead wires on the probe.
Yeah, thanks, Bill.
Now, repeatability, the best sensors are going to have a very good repeatability where we'll get that same measurement over and over again. We can kind of show this, the relationship between accuracy and repeatability here with this illustration. If we shoot an arrow at the target and we hit it, we're probably just lucky. And if we shoot at the target and kind of hit right around the bullseye, we're pretty accurate. If we do that and we hit around the outside but we're hitting the same place, that's the definition of repeatable. Now, if we want to put both of those together and say that we're accurate and repeatable, we're going to be hitting the bullseye time and time again, rather than just having it, bunched in one location or another. that gives us the best of both. It's both accurate and repeatable. And that's really what we're looking for, and not just from the sensor, but the installation errors also play a big role in this accuracy equation. One of the other important things to be aware of is the time response of the sensor as it's installed in the process. If we have a process that's changing temperature rapidly and our sensor can't keep up to that, that can introduce a very large error into your measurement or into your process loop. Some of the things that can be done to address time response would be usually smaller probes that will have faster heat transfer, sensors that are directly immersed into the process. They won't have a separable Thermowell associated with them. And there are some different materials that can be used for the probe, and then some different ways that the probe can be mounted into that process.
And Bill, as far as time response goes, is a faster time response always, I guess, better, or are there times when a slower response is maybe what you're looking for?
Well, and again, that kind of depends. It's sometimes slower is better. For example, if you have a storage freezer or incubator where product is being placed in and out of this thing and the doors opening and closing, you're not going to want that sensor to respond rapidly enough to show that, okay, this freezer door was open for 30 seconds while they put a tray full of product in there and then close the door. You don't want that alarm going off for that kind of a situation. So there you're going to want a time response that is matched to whatever is happening in that process, so that in this case you'd want to avoid that that alarm going off for just opening the freezer door for 30 seconds or maybe a minute. And on the other hand, some processes, if they're changing rapidly and you need to know about that because it's a heater controlling that fluid and it's got to be at that exact temperature to produce a good product, then you're going to need that fast response sensor. So it can play either way. Next up, I want to talk about some of the key factors for probe selection and the installation. And I've got these divided into kind of 4 categories here. The sensor, and there we have the interchangeability to take into consideration, the stability and repeatability of the probe. And as we saw earlier in our little example, that we want the best accuracy and repeatability that we can get out of the particular sensor. Now, some of the larger error sources are actually associated with the installation. And of those, I just pulled out a couple of the ones that I run into as some of the larger ones is with time response, and then stem conduction, which comes about due to insufficient immersion length or improperly designed piping system, or maybe a misapplied sensor type. Then also we'll show how the ambient conditions can play an effect on the accuracy of your measurement. And now after we get all this piping designed correctly and we get the right sensor installed, we need to be able to maintain that sensor. It may be necessary to remove it for frequent calibration, and you don't want to open up your piping system, so there's ways to do that. If a sensor should ever fail, replacing it's got to be easy. And then finally, cost is always one of the big items here. And our real goal with all this is to just achieve the lowest life cycle cost. And that life cycle is not only referring to the sensor, but to that measurement point where that sensor is controlling how much energy is being used to control that process. And you need to minimize the calibration cycles, how often the probe is replaced due to failure or might be just on a regular maintenance cycle. But all those things come into play in that accounting equation to make sure you achieve the lowest life cycle cost. A couple others here too would be for improving accuracy, the calibration where we can actually match the RTD to a transmitter, or you can do a loop calibration. So you would have your, well, maybe a chart recorder, you got the RTD, there might be a transmitter involved, and calibrating that whole system or that whole measurement loop can improve accuracy. And finally, some of the instrumentation comes into play where transmitter, controller, PLCs, those all have some potential errors involved with them, so we need to make sure we choose the correct items there for our to meet our measurement budget. Now, when we some of the things that we can define as a good installation, again, we've got the accurate and repeatable measurement, and that's going to result in high quality product, you know, a good use of energy. And if we do this wrong, it can compromise product quality, and it's also going to add uncertainty to your measurement point. And the uncertainties would go into your measurement error budget or calculations that would be done for that particular location. Now, I wanted to finally here, the last thing I want to get into is the application and installation. This is probably the more important stuff out of the whole presentation today. You know, before I dive into this, I would like to just ask if anybody had any questions. And I don't know, Jeff, is there anything we could go through now?
Yeah, if anyone does have any questions, by all means, go ahead and type them into the Q&A or the chat box, and we'll try to answer them kind of on the fly as we go. So if there's anything that's unclear, you want some additional information on, go ahead and type that in, and we'll get to you just as quickly as we can.
Okay. Okay. So now we've kind of completed a lot of the background information here. I wanted to look at just some kind of traditional installations here. A surface mount sensor can be a potential solution to measuring a small diameter line. The direct immersion sensors work well. And then there are some ways to use Thermowells for measuring temperature in small diameter lines, and we'll look at some examples there. Now, one of the big problems with small diameter lines is the stem conduction or immersion error. And what is happening with this is that the temperature measurement is being affected by the ambient conditions. You know, for example, if we have a process here that's maybe running at, you know, say 121 degrees C, and our ambient conditions are 85, or, you know, room temperature 20 degrees C. So we've got that delta of 100 degree C difference. And the external portions of the sensor assembly kind of act as a bit of a radiator for the that particular point. And so we're going to have heat conducting along not only the metal Thermowell in the probe, but the actual lead wires in the probe. And that's going to affect the measurement if there is not sufficient immersion length into the process to overcome those errors. You know, one of the ways to help minimize this is to install these sensors in a T. You know, if we have like a 1-inch line, one possibility would be just to stick the probe into an outlet in a T, and so we have the fluid coming by it. And this is kind of my, you know, it's an acceptable way to do it. It just is not the best way. Something that'd be a little better would be to install it into the run of the T, so we've got the flow coming up here. The one drawback with this type of installation is that you have a little bit of a dead lag back here in a standard pipe T, and this fluid doesn't always get cleaned out very well. And if you're running a CIP system, this is not going to get flushed out very well. The better location would be to have the fluid coming directly up the tip of the sensor. And that way we get a lot of good washout back here in this kind of stagnant portion of the tee. And we can run this sensor down the run of the pipe with sufficient immersion so that we would get a good accurate measurement and we minimize the effects of stem conduction. So with a direct immersion style like that, we've got some advantages and disadvantages. We can have a real fast response time. We don't have that Thermowell around the probe, so it's just eighth-inch diameter probe or quarter-inch, and they do have a very fast response time. We can get the proper immersion length. The ambient conditions are not going to be much of a factor. Installation is very simple, and they're low cost. You don't have that added cost of a thermal well. Some of the disadvantages here, if you need to calibrate that sensor, you need to drain the system, and then you're going to be opening it up in some pharmaceutical applications. That's not desirable. You want to be able to keep those systems closed so that they don't have to be re-cleaned if they are opened. Now, if we introduce a thermal well into that sanitary elbow diagram that we just had on the screen, this is another way to do this using a custom thermal well and avoiding the direct immersion style probe disadvantages. So we have this elbow thermal well in place, and you can see here we've got thermal well and then the separable probe here that's spring-loaded and fits inside that thermal well. The fluid is coming right at the very tip of the probe, and as you can see back here, there's very little dead lag, if any. And this works really well for small diameter lines from 1/2 inch on up to even 4-inch. For a 4-inch, we might suggest something a little bit different, but we have done installations where that was the desired style of thermal well and probe combination. Now, these can be used either with an RTD or a thermocouple. And again, we'd probably need about a 3.5 inches of immersion here on this style to really provide the best measurement. You can get by with 2.5 inches, and we've got a graph we'll look at a little bit that compares some of these immersion lengths and different sensor and sensor thermal well combinations. So again, the advantages with adding a thermal well like this, we can replace that sensor. We can calibrate the sensor, pull it out. We don't have to drain the system. It stays enclosed. And for a lot of things, that's going to be a huge advantage. You do need to plan this installation fairly carefully because you do need to pick a spot in your piping system where you're making a right angle turn, and the flow rate has to be coming at the tip of the sensor, ideally. It could go the other way, but it's really the best if you have it coming right at the tip of the sensor. So that does require some planning ahead of time for that particular process. Now, if done incorrectly, if we pick an immersion on that thermal well that's not long enough, you can have some stem conduction. And again, cost is going to be a little more expensive, although it's usually just a one-time expense. After these wells are installed, there's really, nothing that's going to wear out unless you have a, corrosive or an erosive fluid running through your piping. So usually it's just it's a one-shot cost to put these types of wells in.
Bill, a couple things. One, just to follow up on what you're talking about with the sanitary wells. Just to point out that it is in fact a sanitary application. You use one of these sanitary wells. The sensor that then goes into that well because it doesn't have product contact, typically is a little less expensive sensor than if you needed to use an actual sanitary with an electropolish finish and a sanitary cap. So something to keep in mind that you go to a little bit more standard sensor when using that elbow well. The other thing, just to point out, if a few people here, if you do have questions, go ahead and type them into the chat box or the Q&A. We've got quite a few people on the line, and so we try to avoid opening up the phone lines. Otherwise, it gets a little noisy. So rather than asking your question, if you could type it into the chat box or the Q&A, would be greatly appreciated.
Okay. Yeah, that's a good point. That the the Thermowell applications typically can use a less expensive style sensor, just because there is no electro polish or high polish required as is required on a direct immersion style. Now, if we can't install anything into the piping, another way to do this is with a surface mount style sensor. And there's a whole bunch of different configurations and things, and I've just pulled a few out of here that are kind of the most common. This one that I show in this installation is just either an aluminum or stainless steel block, and the sensing element is embedded inside that. You can stick it on a pipe with a hose clamp, or any other means that you can think of. And they do work fairly well. They're inexpensive, simple to use. Don't have to modify your piping system. One of the big problems with them, though, is that you're measuring the surface temperature of the pipe and not actually the fluid. And if you're interested in the temperature of the fluid, this is just going to give you a close approximation of what it is. Time response is typically fairly slow with these also, because you've got that. Of course, the pipe has to heat and cool along with the sensor itself. And if you pull this off, go calibrate it and bring it back, you may not get it mounted right in the same exact spot, and so there can be a little bit of difference there. To get the best accuracy out of these, they should also be covered with insulation. One of the solutions to that would be with what we call a non-intrusive style sensor, which is shown here. And this is a sensor, a surface mount sensor, and the insulation is included with this assembly. It's just another stainless steel canister that's welded around the temperature sensor, which is bonded to your process tubing or piping. And that's all sealed up, and so if you have a situation where you're doing washdown or a real clean installation like that, this is a potentially good solution for those types of things. These can be used with line sizes down to 1/4 inch, and again, it's measuring the outside temperature of the pipe and not the actual fluid. So there's a small error there. The magnitude of that error is highly dependent on the fluid flow rate, the ambient conditions, the delta T between your fluid and the ambient conditions. Time response can be a little bit slow, because we've got all that, again, the piping has to change temperature and everything along with the sensor. But you may get for typical installation, you may get a reading that's maybe within a few tenths of a degree of what the actual fluid temperature is. So this can be a good solution. One other area where they get used a lot is if we have a really viscous product or something that's really sticky, that if you had an immersion sensor, that product would build up on it. These can be a good solution for those types of situations.
So, Bill, also, would this also be a good solution if you've got, for whatever reason, extremely high velocity, and you may end up with potentially some damage to an immersion sensor?
Yeah, that would be another potential use for it where, you know, not only high velocity, but if you have a viscous product where you've got a lot of drag, like an immersion style sensor that may cause it to bend or break off, this makes a good solution for those types of things also. Just to review here, advantages, we don't have anything going into the process. Works really well for the really small lines, 1/4 inch on up. The whole sensor is all sealed up. You know, you can wash it down, and if the connection head is in place and tightened up, you know, you're not going to have to worry about moisture getting inside of this sensor and causing a problem. You know, it does have a slow response time, you know, fairly slow. It's maybe 15 seconds, whereas a direct immersion sensor might be down around 3 or 4 seconds. The installation, again, much like the elbow Thermowell, we got to plan ahead, and if you intend to use this, it's a good idea to, when you're doing your piping layout, plan where this thing is going to go. There's a length requirement. I think it's about 8 inches. It's fairly standard for this style. You need a spot to put it, and calibrating these sensors typically can be done in a bath. You know, either an oil bath or, you know, an ice bath is actually a real good way to do these, just to check to see if it has shifted at all. So it can be done. It's just a little more awkward than just a 1/4 inch diameter probe that you stick in your hot block or in a, you know, oil bath and measure it that way. So some of the error sources, I've kind of mentioned some of these previously. The sensor error sources and then installation. With the sensor, there's interchangeability. We've got stability, repeatability, and then there's others like hysteresis, self-heating. If there's any vibration in the system, that can cause some potential error in that sensor. And then there's a few other little ones that usually, you know, they're all down on the, you know, 0.0 something degrees C. But again, installation is really where we got to focus our attention when we're measuring temperature in small diameter lines. Again, stem conduction is the biggest source. Time response can be a big one. Ambient conditions, like we've had situations where you know, we have a proper sensor in the piping and it's reading correctly, and then all of a sudden something happens and it's reading the temperature that's too low all of a sudden. And after doing a little question and answer with the end user, we found out that there was a situation where a fan had been turned on and it was blowing on that location where the sensor was installed, and that was enough to cause, you know, a 0.5 degree C error in that particular measurement. And the solution was just to redirect the fan so it wasn't blowing on that sensor location. So there are things like that where, you know, we talk about ambient conditions affecting the accuracy, and it's things like that that can be a problem. If there's a you know, something else, you know, sunshine, you know, when you get kind of a radiation error, that can be another potential error source. I wanted to look again here at time response and just compare some of the different style probes. And this graph is really hard to read, but because there's probably a little too much information on here almost. But I just wanted to show a kind of a gross comparison between the different style sensors. We have over here a direct immersion sensor, and here we can see that our time response, which is, this is expressed as a percentage of the step change in temperature. So if we're changing from 0 to 100 degrees C, for example, we get up here, and after just, you know, a few seconds with this direct immersion, we're going to be be indicating almost 100% of that change in temperature. And if we come down here and we look at our worst case scenario, which is a quarter-inch diameter probe that was installed into a Thermowell that has a .305 bore diameter, so it's a very sloppy fit. So you've got a little bit of airspace between the probe and the Thermowell, and that's going to slow down the response time. And you can see we're out here at 100 seconds and we're still not up to 70% of the actual temperature. And then there's everything in between. The dashed line here represents a surface mount sensor. The red dots here, this is a RTD quarter-inch diameter in a Thermowell that has the correct 0.26-inch diameter bore size. And again, it takes a while for the sensor to indicate a full temperature change. Stem conduction. Again, this is just the effects of the ambient conditions on the sensing element. And again, this is the biggest problem that I run into, insufficient immersion length. And now this immersion length has to be balanced, with your flow rates and things, so that, if you have a high flow rate, you don't want the probe to start vibrating or cause enough drag on it to cause it to bend or break off. So there's a balance between getting sufficient immersion to overcome the stem conduction versus keeping it safe and viable for that particular flow rate and process fluid conditions.
And if you want to stay there just for a minute, Bill, I think it's just important to point out that immersion length or lack of immersion is, as Bill mentioned, one of the biggest issues that we find with inaccurate temperature measurements. But it becomes particularly important with the small diameter lines, because the traditional way of putting a sensor in perpendicular to the line suddenly becomes a problem, because if you get enough immersion for a good sensor, you're either touching the other side of the tube or the pipe, or you're actually even beyond that. So this is where people will say, well, just give me something really short. Give me something that's a half-inch long. And while that fixes the problem from a flow perspective, now what you start to measure is much more of the outside temperature and the temperature of the outer pipe. You're really not getting a measurement of the material itself. And so some people say, oh, okay, well, I'll put a longer dead leg on there, and so now I'll have it up 3 inches, and that gives me the immersion, right? And the answer is no, that doesn't necessarily give you the immersion either, because the sensor really needs to be in the flow of the material. So again, there are ways to overcome that, and Bill's already gone through some of those solutions, but just can't stress enough the importance in the small diameter line that you can't just go smaller with it. You need to take into account many different factors in order to make sure you're getting the measurement that you want, not just a measurement, because any sensor will give you a measurement, but you want to make sure it's measuring what you've got going through that pipe, not just the pipe itself.
Right. Yep, that's a good point. So looking at a typical RTD Thermowell assembly here, and this is the stem conduction. This is expressed as as a percentage of the delta T, because if we have, the larger the temperature difference between your process and the ambient conditions, the greater the potential for a significant stem conduction error is. If you have a process that's running at room temperature, you're not going to see a difference unless your process fluid changes, and then you're not going to see as much of a change. But So the bigger that delta T is, the more significant the stem conduction error can be. Now this graph shows for the immersion length of the sensor is here. And for this test, it was done in 3 different temperatures, in an ice bath, 100 degrees C, and a 200 degrees C bath. And you can see there's really not much difference between any of those temperatures. So it's fairly independent of the actual temperature of what you're doing, or of what you're trying to measure. And coming down here, we can see that if we get 2.5 inches, we've got a fairly small error. It's like 1% of the delta T. But really, to get away from the immersion error or stem conduction, we need to get out here to about 4.5 inches of immersion before we get to that point where it's even difficult to measure if there is any conduction error happening. And so for this type of an assembly, 4.5 inches is a good minimum number to use. Now that doesn't mean that you can't use smaller immersions, but to get rid of this error here, like in a standard 2.5-inch immersion Thermowell, whether it's a threaded industrial style well, or if it's a sanitary well that maybe has a tri-clamp connection on it. If you don't have sufficient immersion, or the piping is such that you can't get any more than that, 2.5 would work. You just need to be aware that there is a potential for a small error in some situations. And if you can insulate the outside of the sensor, you can get rid of some of that also.
Say Bill, along those lines, we've got a question from Rick on the insulation and how much insulation is required to eliminate stem conduction.
Well, 3 or 4 inches usually is enough so that you're going to see a significant cut in that error. And it really, no insulation is going to be perfect. So we can say, well, more is always better. Within our attics we've got 2 feet of insulation, and that's good. And then they come along and say, well, gee, if you had 3 feet, it's going to be even better. So about all we can say is that more is always better, but 3 or 4 inches usually takes care of most of that conduction error. Now this graph I have up here now is it's comparing the installation effects, it's showing the installation effects of the different style sensors. I just wanted to run through a couple of these. This is a surface sensor, and it's just stuck on a pipe. No insulation, and we've got this again, errors expressed as a percentage of delta T. So we're like a huge error here, 10% of delta T. So if we got a 100-degree difference between our process and the ambient, we got a 10-degree error. That's pretty significant. And then going down to the other extreme here with a direct immersion sensor, with a proper immersion length, we have almost no stem conduction error. And we can look at some of these others, like if we had that elbow-style Thermowell, for example, with a 1/4-inch diameter probe, very small errors associated with the installation. And we can even get rid of that with a tip-sensitive sensor in that elbow-style Thermowell. And this is, again, down in that area where it's even difficult to measure if there is any stem conduction due to the installation. Here we just have a few, we can just look at some of these. Again, the surface sensor is going to be the worst, and then getting down with the tip sensitive, very small error. And even some of these numbers here, when we're down less than 1%, there's a little bit of uncertainty into if we're even able to accurately measure those particular stem conduction errors.
So Bill, just a couple questions have come up. Probably good point to answer some of those. One is, do you have a recommended insertion depth chart for different size pipes up to 4 inches, or is there some type of factor or rule of thumb that you can use?
Well, for direct immersion sensors, we have that rule of thumb of 10 times the stem diameter plus the sensitive length of that sensor. So if we have for example, a 1/4 inch diameter sensor, we take that times 10, so that's 2.5 inches, and then most sensing elements have about 1 inch of sensitive length. So we add that to the 2.5, and we get that 3.5 inches of immersion as a minimum. And again, that's just a rule of thumb. It's for most applications, that's going to work just fine. There are some situations where you could maybe get by with a little less, and there are some where you need to actually add more than that. One that I can think of where you would need to add more would be in the situation of air temperature. I had one application where some sensors were installed in a dropped ceiling, and the probes were sticking down below the drop ceiling 5.5 inches. And they weren't giving an accurate representation of what the room air temperature was. Well, it turns out that above that ceiling was, unconditioned space, so it was very hot in the summer, cold in the winter, and there was some conduction happening because of that short immersion length. And the solution there was to go to a much longer probe and have more of that sensor in the conditioned space, and that took care of that situation there. If you have a highly conductive fluid and it's moving at a high rate of speed, you could maybe get by with less than 3.5. But having this 10 times the diameter plus the sensitive length is just a good rule of thumb for direct immersion sensors. The Thermowell situation, having that 4.5 inches, like shown on the graph, is just a good minimum number to use for those.
So in the case of where, say, maybe it's a direct immersion, and you're at 3.5, and you're putting it into a 4-inch pipe or a 3 3/4 inch pipe, how far ideally do you want, if you're putting it in perpendicular, which is the way most people start out? That's a pretty common way to start. Where do you want that sensing element in relation to the opposite wall of the pipe? For the real small diameter lines, like a 1/2 inch and 3/4 inch, even 1 inch, I always recommend that you try to span the full diameter of the run. If you're going through the outlet of a T, to have it come within maybe a 1/16 of an inch of the far wall of the run, so you get the most immersion that you can there. Because you are going to have a little bit of a dead space in an outlet T where the sensor is installed, just because that fluid is not going to circulate quite as rapidly as what we'd like to see. But, for example, in a 1/2 inch line with a short outlet T, I think the minimum sensor length that we found that works well is 1.1 inches. And that'll span just about the full diameter of that 1/2 inch run when it's installed in a short outlet T. Right. And that is with an 1/8 inch diameter sensor, right? You try to go down in the diameter of the sensor as well if you need shorter lengths.
Correct. Yep. Yeah, we do get less stem conduction with smaller diameter sensors, small diameter internal lead wires, just to minimize the path through anything that's thermally conductive. So I guess we've covered probably everything that was on this slide that I was going to talk about next with that question. So that was a good question. One of the other things, well, again, the insulation. We haven't talked about heat transfer compound yet, though. Now, this is something that can be used. You know, in some situations, it's not desirable because, you know, if you do have a failure or something, you just, you know, like if it's in a Thermowell, for example, you know, and it breaks, you could get that stuff into your process, and it, you know, it could be a bit of a headache to get cleaned out of a full system, like in a pharmaceutical application, for example, or some other process where you don't want, you know, you want to minimize whatever contaminants are getting in there. But for those situations where it is allowable, it does really help speed up the response time, but it also can help minimize some of the stem conduction by concentrating that heat transfer between the tip of the sensor, where the sensing element is, and the Thermowell that the sensor is installed in. I had mentioned balancing the immersion length with a safe flow velocity, you know, because if we put a sensor in a pipeline and run a fluid past it, and if we get it at too high a rate, that probe can actually start to vibrate, or it can bend just from the drag on the probe. This chart shows for a 1/4 inch diameter sensor down here, this would be like a direct immersion style sensor, 4 inches of immersion. We got about, you know, maybe 30 feet per second is a safe flow velocity. If you go over that with that particular immersion length of 4 inches, it can start to vibrate. Worst case, it's going to break off and head on downstream and really screw up something. So you really need to be aware of, you know, not only that stem conduction issue and getting in as much immersion length as you can, but we need to look at that flow rate to make sure that it's not going to be so high that it's going to cause other problems. This is a typical direct immersion style sanitary sensor. This particular one shows a 1/2 inch tri-clamp fitting. And this is a real common way of measuring temperature, either in a short outlet T, we can go, you know, perpendicular to the flow, or if it can be installed in the run of a T, that's a better situation. This is a similar sensor to that, although it adds a separable Thermowell. This particular one, I believe, is the Thermowell is 3/16 inch diameter. That's this portion right here. And the temperature probe is 1/8 inch diameter. So it's a fairly tight fit up inside there. This will allow you to keep your process closed up. You can remove the sensor by just breaking the pipe union here, and the sensor connection head will pull right out of that particular well. So this is a good application where if you've got a small diameter line, you want to keep your system closed up when you're calibrating the sensor or for replacements. This is a real good solution for that. This is a 45-degree sanitary elbow where a sensor has been installed directly into that sensor. So if this were ever to fail, or if you calibrate it, you got to pull this whole thing out of the line and calibrate it in a bath of some kind. And if the sensor fails, you're replacing the whole elbow plus the sensor. But it is a good solution for places where we can't get anything else to work correctly. The sensor in this situation is about 80 thousandths diameter, and it immerses into the elbow, kind of pointing right directly into the flow, just over 1 inch. So it gives fast time response, fairly cleanable situation, unless you get that viscous or sticky type product, and this would not be such a good situation. But for some applications, this would be a style that you could look at. Again, this is a typical sanitary elbow Thermowell for 1/2-inch diameter tubing, and it has the 1/2-inch tri-clamps for the process connections. And a spring-loaded sensor that fits into that well with an extension cable on it.
Hey, Bill, there was a question on elbow wells and pressure ratings, and just wondering, what are the typical pressure ratings for those elbow wells? Would they handle something up to 5,000 psi?
5,000, depending on, it would have to be custom designed to handle 5,000. These are typically designed for 100 psi or lower, where just kind of your typical pharmaceutical type applications. None of those are really ever really high pressure, but depending on what kind of tubing the rest of the piping system is made from, we can match up that same that same material, wall thickness, whatever, and one could be designed that would work in that type of situation. We show it here with tri-clamp connections. There are weld ends, and I suppose pretty much anything else could be put on there on a custom basis. But its main use is with sanitary applications, whether it's pharmacy, food, beverage, or similar type situations. Another sensor that may work well in that, the 5,000 psi could be something like this, where it's replacing a section of the piping, and we just have to put the correct style connections on it to handle that pressure. Again, a non-intrusive sensor like this is a real good way to get into an even smaller line, like a 1/4-inch diameter on up. And it's a surface measurement, but you're going to get fairly close, maybe within a few tenths of a degree of the actual temperature of the fluid. And finally here, I think this is the last one, where we're just looking at either a stainless steel or aluminum block. It has a nice radius cut on it to conform to the radius of the tube or pipe that it's attached to. This would just be held on with a hose clamp. You can get a little faster time response and a little more accurate measurement by adding a heat transfer paste right along this surface, and then wrap it with insulation. Probably a 3 or a 4-inch thick blanket of insulation around it is typically sufficient to minimize the effects of the ambient conditions. So just to summarize real quick here, it looks like we're actually running short of time. I should have talked faster, huh? So some of the things that when you're doing small diameter lines and you need an accurate measurement is get the instrumentation involved early on in the piping design process, so that a proper location can be identified to install the sensor, and have the sensor picked out ahead of time so that it can be built right into that layout. It happens time and again where we have to go into an existing system and we have to make compromises with accuracy just because of the way the piping was done. And it's at a situation where it can't be changed later on. So it's really important to get involved ahead of time. When we do that, we get that good measurement accuracy. We've got really efficient use of our energy resources, and we're going to be producing that high quality product consistently. So, and I guess we've gone through quite a few questions already. I don't know if there's any others here that we can do real quick.
I think we've got a couple more, but just want to remind people, if you do have questions, go ahead and type them into the chat box or the Q&A, and we'll attempt to get to those questions as we can. Also, want to let folks know before you sign off, when you exit out of the WebEx here, you will be taken to a landing page for RTDology, and from that page you can download. You'll see right on there where you can access a downloadable version of a white paper on small diameter lines. So it goes over into a little bit more detail what Bill covered today, but it's a good reference either for yourself or maybe for some colleagues who weren't able to attend. So I would highly recommend when you get to that landing page, go ahead and download that paper, as well as just a reminder, we will send out a link to the recording and also a copy of the presentation notes, and you'll get those within the next 24 to 48 hours. So from a question perspective, we have a question as to what do you recommend for heat transfer medium for sanitary applications? Ooh, there's a good one.
You know, we use a it's a zinc oxide silicon oil paste, which it's very similar to what is used to heat sink IC chips on circuit boards, and that works fairly well. I mean, there's others out there. You know, anything that you know, I guess I don't know of anything specific that would be compatible with sanitary applications other than well, I guess I don't know the heat transfer capabilities of the grease that they use on a lot of the equipment that's used around like the food beverage type industries. But typically anything that can take up that air gap, because air is not a very good conveyor of heat. So when you got a temperature probe Thermowell application, we just minimize that space with, and you know, some of the industrial applications that will use like an oil or something to take up that air gap, and it's going to depend on, you know, with the oil, the well almost has to be installed vertically, so of course it doesn't all run out. The paste stuff that we use is thick enough so that it doesn't run, so it can be mounted in any location. So yeah, I really don't have any other recommendations other than kind of a zinc oxide paste with good heat transfer capabilities.
Okay, we've got another question. What would you recommend in a gas application? I guess I'm not sure exactly what that refers to, but maybe just a, you know, from what you've talked about today, Bill, whether it's a liquid or gas, what items still apply, and what might you need to do or look at a little bit differently if it's a gas versus a liquid?
Yeah, for gas type applications, there's, you know, time response can be a big issue there because the typical RTD is going to have a pretty slow time response. It may be a situation where a thermocouple, very small diameter, may be a better choice just to overcome that time response issue, and it would actually give you a more accurate measurement because of that. You know, I mentioned that example of measuring room air temperature, and we typically need a little more immersion length and be a little more cautious about minimizing the stem conduction issue. And again, there, a very tip-sensitive thermocouple could be the best technology to use to do that.
Okay. Well, unfortunately, our time is up. We went a few minutes over. We apologize for that. If we did not get to your question, or if you would like to further discuss a temperature measurement problem or application, please do go ahead and give us a call directly, and we will do what we can to help you out. We want to thank you for attending. We look forward to seeing you at future events. And as a reminder, again, we will be sending out session notes and a link to the recording within the next 24 to 48 hours. So with that, have a great afternoon, and we hope to see you next time.